Good afternoon, Professor. I'm Chen Quing from Munsang College, Hong Kong Island. My research is called Capture King, which is a mathematics game I create. In the following, I will introduce the games to you, discuss the mathematics on the winning conditions, and talk about the strategies for winning the game. However, I'm sorry that some results in my report are incomplete and I've improved them. So some of the results you see in the PowerPoint may be different from those in my report. Let's begin with the game's rules and the winning condition. First, every player gets 20 cards including 2 pieces of 0, 1, 2 to 9. Next, the player randomly removes 6 cards from the card sets of their opponents. Then a king, which represents 5 pawns, is added to each set. After that, they can start to play. The game has totally 7 rounds. The player must select 1 to 3 cards from the available cards for playing each round. The card sets with the largest sum in each round will win the game. If the card set with a king is not the winner in that one, it will be captured by the winner. Otherwise, the king can escape. The first winning condition is that the one who has the most king will win the game. If the player draws in the first condition, we compare the number of winning rounds and the compensation value, which are divided as the sum of cards removed at first divided by 11. I will explain it in the second part of my presentation. If the first 2 conditions cannot find the winner, the player will draw. For example, assume that the blue and the green comes to the second condition. The blue one will win the game if the compensation value has not been introduced, since he won 4 rounds. However, the green finally wins the game after introducing the compensation value. Since the more powerful cards are removed, the higher compensation value he gets. For easier expression, I would like to define some symbols. S13 with king K means the sum of the 3 cards including a king in round 1. B refers to the 20 cards before the remove stage. B1 is a subset of B, represents the 14 remaining cards. B2 is another subset of B, represents the 6 removed cards. L is the compensation value. P is the number of the players. The player will win the game if one gets the most king. Therefore, the most important strategy is to capture others' king and to save your own king. Since only 1 to 3 cards are allowed, the maximum value of S3 is with king is 9 plus 9 plus 5, which equals 23. So king must be captured when Sn larger than 23, and Sn must be S3 equals 24, 25, or 26, since there are 2 pieces of 0, 0, 1, 2 to 9. And by counting, there are 2,850 possible outcomes of B2. For example, there are about 50 sets of B2, adding up to 16. There are 357, 1,908, and 585 possible outcomes of 2 sets, 1 set, and 0 sets of S3 larger than S23 respectively. Therefore, I can conclude that the probability of capturing at least a king, assuming that the player uses the most powerful S3 larger than 23, should be equal to the following equation, where the constant behind the represents the probability of S3 loss, such as 23 cannot win 25 or 26. I can find these results when different number of players join the game. It confirms that we better capture the king from the opponents if there are 4 players, like the green verse. We do not discuss the cases without using the most powerful cards to capture others' king, since the select point is mentally but not randomly, which is impossible to define in mathematics. But the probability of capturing a king should be larger because it equals to P capturing a king, assuming that the player uses the most powerful S3 larger than 23 plus P capturing a king without using the most powerful S3. So, the actual value of P capturing a king should be larger than that I find, and P escape should be smaller. Now, I'm going to talk about the compensation value, L. To let capture king become a fair game, I introduce L. Without introducing L, the unfair situation may appear. For example, the blue player gets 3, 3, 4, 4 up to 9, 9, and the green player gets 0, 0, 1, 1 up to 6, 6. It is no doubt that the blue player must win the game without L. To make the game fair, I believe that given the set B2, the expected number of round 1 by the blue player plus sum of J1 to J6 times L should be approximately to a constant. For easier calculation, assume that each player groups his cards in such a way that 2 strongest cards are used together with the king in first one, and then the 2 strongest ones in the remaining cards are used in other ones, etc. Let Sij be the sum of the cards given by the blue player in different rounds, and Tij represents the green players. Given set B2 of the 6 blue cards removed at the beginning, the expected number of the round 1 by the blue player is equal to the sum of the probability of Sij wins. The following is an example in which the blue player has the strongest card set and green has the weakest card set. In such case, expected number of the round 1 by the blue player is 40 over 7, which is close to 6. Of course, the above example is only an extreme case. In general, I think that given that set B2, the expected number of round 1 by the B player should approximately equal to the expected number of round 1 by the B player against G1 median. Through some tedious work, I find that 1 over L is approximately equal to 11.6, 12.1, 13.5 when there are 2, 3, and 4 players respectively. So we should choose 1 over L between 11.6 and 13.5. However, the smaller value of 1 over L is better for the less powerful card sets. Besides, since it is more difficult for the less powerful card sets to go into the second condition, I have chosen 1 over L be 11, which is an integer and smaller than 11.6. Time is running short. I think I have to stop here. Thank you.